This video gets you started using SystemVerilog cover groups for data coverage. Imagine a tiny 3-node office-sized packet network. Packet addresses are between 0 and 2. The packet data payload is between 1 and 63 bytes. The packet has a data parity byte. 10% of the packets will have corrupted parity. Let us first define the packet properties and constraints. To represent an ephemeral object as a class is common, so we will do just that. We define the following class properties: a 2-bit random address, an 8-bit random payload of random length, an 8-bit parity that is not random, and a 1-bit packet type that is by default good and can be made bad. We define the following constraints: address to be between 0 and 2, payload size to be between 1 and 63, and type to be 90% good and 10% bad. As a post-randomization activity, we generate the parity. And there we have it. Let us now, within the class declaration, declare and construct a SystemVerilog cover group to detect what types and sizes of packets the test sends to what addresses. We start the cover group declaration with the cover group keyword, followed by the cover group's type name. A cover group declaration is a type declaration. To reuse the same cover group declaration with multiple signal sets, we can then include a task or function port list. As you can construct a cover group declaration embedded within a class declaration only once, a port list here is less useful. To automatically sample covered expressions, we can include a coverage event. For scope variables, the coverage event is usually just the active clock edge. As classes appear frequently in unclocked systems, we elect to instead call the cover group's sample method to explicitly sample the covered expressions as needed. We then, immediately, before we forget it, set the cover group's structure option field per instance to 1. This stores sample counts on a per cover group instance basis. The assimilator, by default, stores sample counts on only a per cover group type basis. The per instance data is not available, so the reporting tool cannot show it, and will not remind you that you forgot to set the per instance field. We declare a cover point to cover the packet address. We start the cover point declaration with an optional identifier, which is not so optional if you want to be able to later refer by name to the cover point, followed by the cover point keyword, and then followed by the expression to cover, here, the address property. We can optionally include a guard expression to suppress cover point sampling. The assimilator automatically creates up to 64 counters, called bins, to count the occurrences of unique values. You can change that default number. For more than 64 unique values, the simulator, as evenly as possible, distributes the unique values, with the last bin counting the extra values. If the automatically created bins satisfy you, then you can terminate the cover point declaration right here with a semicolon. We will instead go ahead to define our own bins inside a set of curly braces. we can start a bin definition with the wildcard bin modifier keyword. The wildcard keyword interprets specified high impedance and unknown values to mean that the counter should increment if that bit position of the covered expression is either 0 or 1. Without the wildcard keyword, the counter increments only when that bit position of the covered expression is actually that specified high impedance or unknown value. We do not use the wildcard keyword here. We then use the bins keyword to indicate a normal bin, followed by a bin identifier. We vector the bin and do not limit the vector size. The assimilator creates up to 64 bin elements to individually count unique values. You can change that number. For more than 64 unique values, the assimilator, as evenly as possible, distributes the unique values, with the last bin counting the extra values. If you limit the vector size, then the distribution is of list entries instead of unique list values. We follow that with the range list, which here is the values 0, 1, and 2. So the simulator creates 3 bin vector elements to individually count occurrences of the values 0, 1, and 2. We can likewise optionally include a guard expression to guard just this bin. Here, we do not guard the bin. Along with normal bins, you can define ignore bins and illegal bins. The assimilator ignores values assigned to ignore bins, even if they also appear in a normal bin. The assimilator reports as an error the occurrence of values assigned to illegal bins, even if they also appear in an ignore bin or in a normal bin. Here, as we have explicitly binned all legal addresses, we bin all remaining addresses into an illegal bin, so that the simulator will report their occurrence as an error. Note at this point that all the bin's keywords are plural. It is very common for a person to enter a bin's keyword as singular, especially if it truly is only one bin. The mistake may take some time to diagnose. We close this bin definition with a right curly bracket. For the payload size, we likewise define a bin for the small sizes 1 to 31, another bin for the large sizes 32 to 63, and an illegal bin for all other sizes. For the packet type, as the only 2 possible values are both legal, and we will not later refer by name to the bins, we will rely upon automatic bin generation. We start the cover cross declaration with an optional identifier, followed by the cross keyword, and then followed by the list of 2 or more cross items, which can be variables or declared cover points. Here, we are crossing the packet type and packet address. We can optionally include a guard expression to guard the cross. Here, we do not guard the cross. The assimilator, by default, creates a bin for each cross product. If the automatically created bins satisfy you, then you can terminate the cross declaration right here with a semicolon. We will instead go ahead to define our own bins inside a set of curly braces. We then immediately, before we forget it, include a commented out setting to disable displaying automatic cross bins. This feature needs further explanation, and here it is. For a cover point with user-defined bins, the assimilator does not continue to automatically generate bins. For a cover cross with user-defined bins, the simulator does continue to automatically generate bins for those cross products that do not appear in the user-defined bins. The SystemVerilog standard requires this. As an extension to this standard, Cadence Design Systems adds to the cover cross structure option the field Cross Auto Bin Max. Setting it to 0 disables automatically generating those extra cross bins. We want to ensure that the test sent good packets and bad packets to all addresses. To do that, we can rely upon the automatically generated cross bins. However, if we rely upon the automatically generated cross bins, then we will not learn how to define our own cross bins, will we? So we start the cross bin definition with a bins keyword, an identifier, the assignment operator, and a selection of cover point bins to participate in that cross bin. You can then, if you want to, include a guard expression to guard just that bin. Here, we do not guard the bin. Note that you cannot vector a cross bin. If you want an iteration of multiple cross bins, then you must define each and every one. The selection expression is an expression of variables or cover points or even cover point bins, optionally filtered to just those bins that represent certain values, and negated, conjoined, or disjoined as needed. Here, we define a cross bin that counts the occurrences of good packets sent to address 0. And we likewise define a cross bin that counts the occurrences of bad packets sent to address 1. You can continue in that manner, or, as we have already discussed, as the automatically generated cross bins suit our purposes, we could just rely upon them entirely. And there we have it. One more thing though. Recall that a cover group declaration is just a type declaration. To collect coverage data, you need to actually construct a cover group object. For a cover group declaration embedded within a class, to construct the cover group object within the class constructor is very common. So that is what we do. Note that for a cover group declaration embedded within a class, you do not separately declare the cover group handle. As you can construct the cover group at most once anyway, the cover group type name is also its instance name. Here, the Integrated Metrics Center displays the cross-product bins. The test hit most cross-product bins. The number of bad packets is approximately 10% of the number of total packets. The Integrated Metrics Center displays the user-defined cross-product bins, and then, for any cover point values that those bins do not represent, also displays the automatically generated bins. With the option structure, Cross Auto Bin Max field, a Cadence Design Systems extension, you can elect to not record those automatically generated bins.